Hello, everyone. Welcome to IS 300 and today's discussion of Chapter 8, Virtualization Technology, and Security Guidance, Domain 8, which also talks about securing virtual environments. In this discussion, we will talk about virtual machine technology, applications in an enterprise, the pitfalls of virtualization, and when we get to security guidance, we will talk about securing an environment of virtual machines. In this week's reading, both assigned reading materials, both of them agree that the most influential technology that has enabled cloud computing is virtualization. Simply put, it allows users to simultaneously interact with the computer system as though they have the entire virtual machine, the entire system, if you will, to themselves. User processes on one system, on one VM virtual machine, are oblivious to other processes on other virtual machines. The engine that drives these virtual machines is called a virtual machine monitor, VMM, also known as a hypervisor. Virtual machines can run independent operating systems. For example, you can have Windows, Linux, all on the same virtual machine. Different operating systems, different versions of an instance of a virtual machine. Here's an example of 3 different types of virtual machine technologies. The first one talks about process virtual machines. Then we have system virtual machines, host system virtual machines, and native virtual machines. The difference being is that in a process virtual machine, you have the hardware, then you have an operating system, and then you have multiple virtual machines, each running their own application. In a system host virtual machine, you have an operating system, but you also have one or more guest operating systems. And in a native system virtual machine, you have the operating systems, but the native virtual machine does not require a host operating system, as these two do. So this one has an operating system, this one has an underlying operating system, but the virtual machine is a native virtual machine, and the host operating system runs directly on the physical machine. And you may have one or more guest operating systems that are also running on this system virtual machine. Processes under an operating system are allowed access to the hardware through system calls, what we used to refer to as remote procedure calls. The hypervisors, or the VMMs, virtual machine monitors, enable a full hardware instruction for every virtual machine. Every system virtual machine can run a full operating system while staying isolated from other virtual machines. And because virtualization allows each user process to access system resources oblivious of other processes, this is a concept that is referred to as virtualization. You may have heard For example, a Java virtual machine, which is a very common virtual machine, which runs on as an operating system itself, but it's independent, system independent of the machine that it's running on, written in Java. And those operating systems that it calls, that's typically the definition of a process virtual machine. Then there's a concept called elastic computing, the ability, of course, to expand and collapse, or to increase and decrease, just like a rubber band, to give more capability, processing, memory, storage on demand. Key is on demand. Provisioning of these virtual machines, elastic virtual machines, is achieved through automation. So you set up, using APIs and scripts, a way to increase or decrease dynamically based on demand. Amazon's cloud computing, or Amazon's EC2, is an example, running tens of thousands of servers, and each one of them independent of each other because of virtual machine technology. Provisioning of these machines is automated. Automation is the key to elastic computing in a virtual environment. Processes under a virtual machine are allowed access through system calls. System virtual machines have to provide a full set of hardware instructions for each virtual machine. Virtual machine running on one physical machine can be transferred or migrated to a different virtual machine. Its state, or the state of that virtual machine at any snapshot in time, can be suspended, saved, and transported to a different physical machine. So if there's a hardware failure, for example, you take the virtual machine off the machine that failed, and you load it onto the machine that's running, transparent to the user, no harm done, and it basically involves capturing and copying the entire state of the machine at any given time, including the processor, the memory, all hardware resources, BIOS, network MAC addresses, and things like that. So it's very easy in an environment, in a virtual machine environment, to take the problem and move to a different piece of hardware and keep running. The good news is security incidents can be traced fairly easily because you have better diagnostics. You can simply copy the virtual machine, and then you have all the time you need to diagnose what has happened without disrupting anything. It's non-disruptive. Services can continue, but you have the ability to retrace, to look at and examine, analyze whatever happened in a non-disruptive environment. And so security incidents can be recreated and traced. That's the good news. The bad news, though, is that if there is a successful attack, then that attack can spread more rapidly in a virtual environment. The key is not to allow an attack to occur in the first place. So you use replication You have one or more replications of a server in a database. Fault tolerance is part of it. It's critical to be fault tolerant in virtual environments, just like in any other environment, of course. But if you do have replication, then and you're replicating on the same physical device, which of course is not a good idea. But if one virtual server fails, they're both on the same physical device, then that defeats the whole purpose of replication. So the idea, of course, is to have virtual hardware or redundant hardware and software. There are two approaches to desktop virtualization. First, you can deploy all clients as virtual machines. And a lot of companies are now doing this. I work for a company and I log on to Amazon Web Services and spend all my working hours using a virtual machine, using the web through that virtual machine, and my host operating system is not involved. Once I log into the Amazon workstation, I am basically in a different environment altogether, including any web activity or anything of that nature. It's all captured in the virtual machine, but my machine is untouched. You can also have application streaming, which simply means that you take a virtual image, you maintain the virtual image centrally, but you run the applications on the client. So of course, these are not thin clients. These are clients with the capability to run an application on them. Consolidating servers is a common way to reduce something that we call server sprawl. You have so many servers that it's very difficult to maintain them. If you consolidate, then it becomes more efficient, of course. It reduces the complexity, and it allows you to monitor and to manage more effectively. You can use some of the queuing theory formulas that we looked at in this module. Fortunately, we have software that calculates using these formulas. You can input a number of variables, the number of processors, the power consumption, the clock speed. You can do some what-if analysis, and you can do that fairly efficiently, and then determine what the optimal configuration is to achieve the maximum response time. Automation is critical in virtual environments, of course. You have 4 different levels of automation as identified in the textbook. Basically, level 0 is virtual images. You take an image, you deploy that image across all of your various clients as needed. Very common level 0 virtual images. You also have integrated provisioning, which allows you to create new servers, new network resources, storage area networks, and things like that through a single interface. That's level 2. That's more for administrators. Then level 3, elastic provisioning, which is, of course, the automation. So you have a lot of programmatical provisioning of applications. And once the overhead is at the beginning of the automation process. But the good news is that once you have that automation in place, it's very easy then to migrate. Level 3, it's becoming more common now. Load balancing, security, co-location, fault tolerance, fault recovery. All of these things are now becoming more commonplace in level 3 automation infrastructure environments. So that takes us to security guidance. The other PowerPoint presentation that I'll cover today. This is Domain 8, Security Guidance, Domain 8, Virtualization Technology. Very simple. There's an introduction, an overview, and some recommendations. I like the security guidance. It is a recognized industry standard by a company that offers now a certification and a lot of white papers primarily on cloud security. We will spend more time looking at their work. Virtualization, as was said in the first reading assignment, the core technology for enabling cloud computing. It gives you fixed infrastructure and it turns it into pooled resources. For example, computing, or compute is what they call it, network, storage, and containers. Virtual assets are different from the infrastructure that they are abstracted from. Extraction simply means hiding all of the details of the hardware and the processes from the virtual machines. So virtual abstraction takes the resources from the underlying physical assets. Here's probably the big takeaway from this. Without virtualization, there is no cloud. I will say it again. Without virtualization, there is no cloud. So you have, in this discussion, they talk about 2 layers of security controls. You have security for the virtualization environment itself, which includes the hypervisor or the virtual machine monitor, and security controls for all of the virtual assets. So for our first category, which is compute, you abstract the running of the code, the operating system, and all of that from the underlying hardware. Instead of running directly on the hardware as a traditional operating system does, the code runs on an abstraction layer that gives you more flexibility. Cloud providers then are responsible for managing those processes. Memory and all of those things on one virtual machine should not be visible to the other virtual machines in a multi-tenancy environment. And remember, the multi-tenancy environment is simply multiple virtual machines. They could belong to different companies, but they share a cloud vendor, a cloud provider that then provides the underlying infrastructure, and then the customer or the cloud user can then deploy and keep their own virtual machines separate from the other clients using the same vendor. Securing the underlying infrastructure, of course, then becomes critical from internal and external attack. Internal misuse is a big problem. A lot of the attacks, some of the most noticeable, some of the most noted attacks that have happened, cybersecurity attacks in the 21st century, inside jobs. The cloud user, therefore, is responsible for implementing their security in their virtual environment, separate of the other environments that are used on by the cloud provider. The cloud user controls their own stuff, simply put. Cloud users will manage their own virtual infrastructure, especially if it's an IaaS or an infrastructure as a service environment. Now that brings up a good point, because if it's a software as a service environment, then the vendor will probably manage the underlying infrastructure. If it's infrastructure as a service environments, then the cloud user will manage the virtual infrastructure. If it is a platform as a service, the cloud provider will provide the platform, the operating system, and then the cloud user will manage the underlying applications that run on that platform. Security settings, something who can change the virtual machines, who can change the configuration of the virtual machine, very important. Who monitors and keeps tracks of the logs, the event logs and things like that. That's the responsibility of the cloud user. Asset management, who has access to the images and where are those images deployed. Dedicated hosting, making sure that you have a host specifically for your virtual images, ensuring that the deployment is only secure configurations, patched. We will talk when we get to week 11, I believe, about some of the security breaches which were caused as a result of poor patch management. So we will talk about that. Keeping those patches up to date is critical. You put the patched and updated image on a virtual machine, and then you deploy the new image to all of your clients. It makes it very clean and very simple. Networking, of course, has changed very much. We don't have the traditional packet sniffers and troubleshooting, most in a cloud environment anyway. The cloud users do not have access to the raw data packets unless they have tools to collect that data themselves for their own virtual machines, that they cannot see the overall packets and how they're moving around in the underlying physical network, unless they have an agreement which tells them that they can do that. Here's a before and after picture, which I think spells it out pretty clearly. In the old days, the traditional approach, you had a server. In this case, you got server 1 and you got server 2. Between those servers, you have a network. This is plain old networking 101. This is how it looks. The servers communicate with each other through the network. In a virtual environment, you have the physical network underneath, and then you have server 1 with its own set of virtual machines. In this case, there's 1, 2, 3 virtual machines on each server, but the beauty of that is the 2 servers, this probably should be server 2, I'm going to call it server 2. The difference between server 1 and server 2 is that there's never really any physical network that goes between them, but rather within the server and within the virtual machines, there's communication and transmission, but not necessarily between those servers. So the virtual machines on server 1 do not necessarily interact or know anything about the networking or capability of the virtual machines on server 2. Cloud computing supports remote management. You may have had a troubleshooter or an administrator contact you and take over your desktop remotely to look at the configuration and see what was going on. That happens more and more commonly now using the management plane that we talked about last week and the metastructure. Those things are, you must have a management plane and metastructure in order to manage a cloud computing environment remotely. Those of us who telework, we use that configuration on a regular basis. It's possible, of course, the pitfall, easy to create and or destroy network with a handful of API calls. Just a few clicks of a web console, and you can have the entire cloud environment if it is not carefully configured, and or, as I mentioned before, there's a problem because it's an inside job. The provider responsible for detecting and preventing the underlying physical network and virtualization platforms, of course, building a secure network infrastructure and making sure that it's configured properly, disabling packet sniffing, enabling built-in firewalls. But that begs the question, if there is the need to troubleshoot a network. Back in the day, I used to use packet sniffers on the regular to troubleshoot a network. Typically, we would have, if there was an outage, the first thing everybody would point to is, oh, the network is down, the network is causing the problem. We could use the packet sniffer to prove that the data was traveling across the network and it was stopping at a certain server, a certain location. So we knew the data was moving, packets were moving back and forth. They simply were not going any further once they reached their destination. So the only way we could do that, though, was through a packet sniffer. So disabling packet sniffing is kind of a catch-22, but it will keep others, intruders, of course, from looking at the data going across your network. Cloud users configuring their own deployments, they are responsible for that, and any virtual firewalls, compartmentalizing, maybe by work units or by departments, using a template instead of manually configuring settings. You use a template. You deploy the template. It becomes a baseline. Then that baseline can be modified as needed when there is an issue, but the only way you can do that is if you already have a template and or a baseline in place. Keep your copies of data in different locations. If there's a drive failure, of course, you want to have more than one version of the data in multiple locations, so if there's a fire in a building, it doesn't destroy all of your data. And encrypting, of course, very necessary always, both at the drive layer and at the virtualization layer as well. Containers. Simply a virtual execution environment that shares a kernel. Kernel simply a CPU or an operating system that manages memory and CPU time. So you may have multiple virtual environments, multiple virtual machines that share a kernel or, if you will, an operating system. Kernel, just a fancy word for an operating system. The container, make sure that you, of course, since it is the underlying physical infrastructure, that it has to be secured in a secure location, and build the security into those tasks running inside your virtual machine or your container. And don't allow too much network access. Maybe you don't need to give any network access once they connect to the virtual machine. Secure hypervisors, patch management, critical. Keep the hypervisors isolated. Keep the virtual machines isolated. Make sure you have perimeter security, surveillance equipment. Detect against consumers at the physical layer, at the hardware, at the infrastructure layer. Isolate your networks, virtual networks, and use policies to prevent modification and monitoring of traffic without approval of contractual agreements. Next week, we will talk about service level agreements. Those service level agreements are critical in defining the level of security that is, who's responsible for what. The provider is responsible for a certain amount of that security. The user is responsible for a certain amount. The service level agreement will dictate who's responsible for what. It is a legally binding contractual agreement, and it's very critical. So we'll talk about that next week. Encrypt, of course, and isolate your encryption from your data management functions. If you encrypt, then make sure that your administrators who have access to the encryption, they also have checks and balances in place. Not one single administrator should have all encryption keys. The user should make sure that they understand what is being offered by the cloud provider, and if there are any security gaps, clearly you don't want any surprises in cloud environments. Configure the virtualization services using guidance from the provider and, of course, industry best practices. That is our discussion of week 9, which talks about virtualization and virtualization security. Please let me know if you have any questions. Ensure that only known and approved images are available. Make sure that orchestration, which is simply task management, is available, and implement role-based access control and strong authentication. And again, let me know if you have any questions.